So for that, if I also look into this, it will give me what we can do inside each head. Okay, so first of all, we will multiply this q and k. So same steps we are going to follow. Okay, just with a bit difference. Why? Because we will have the shape difference. So here we are going to first of all multiply the q with k transpose, and then we are going to scale it. Okay, so if I come here and simply say scores, these scores are going to be equal to torch dot matml. Okay, and here I will pass the q. Okay, this q, and k dot transpose transpose. Okay, and where I actually want to transpose, I will be transposing it on the last dimension. So say we have this 112, 128, 64 in each head. Okay, so for each head we also have the keys of, so we can just, okay, forget about these first two. Okay, they are not going to contribute in the matrix multiplication. Okay, like this, and these 12 heads are going to be executed parallelly. Okay, so if you now see, we have 128, 64, 128, 64, but for the uh, matrix multiplication, it is important to have this shape where we will have 64 here and 128 here. So when we perform this k transpose, okay, so this is what happens. So it means we are going to perform the transpose on last two dimensions. Okay, so I am going to perform it on -2 and -1. Okay, this will give me the scores. Okay, and please remember, all of these heads with this one line of code, 12 heads are going to be executed at once. Okay, now the scores, I am going to scale them. Okay, how to scale them? Math dot sqrt. Okay, the same formula. Okay, and here I will be doing this head dimension. Okay, so self dot head dimension. Let's see if this is, yeah, self dot head dimension. Okay, so it will scale the scores. Okay, now the next part, if you remember, here as well in the single head, what we did, we performed this masking of the attention mask. Okay, when we multiply this q with k. Okay, so if I just come here and show you this, so after this scaling, if I just return scores, okay, and I just execute it, and let's just check. So this testing will now have the scores, and if I just execute it, you can see it gives us 128, 128. Okay, why? Because we had 112, 128, 64, and we multiplied it with 112, 64, 128. You remember, this is the k and k transpose. Okay, this is the q. So what we get as a result, if the internal values they are same, we get the output of the external values. Okay, so we get 112, 128, 128 as a result. Okay, so that is why you can see 1 128, 128. Okay, so now the attention mask is 128. Okay, this we already know from the previous code for single head attention, but let me just show you that this attention mask, this one, okay, this attention mask is attention mask dot shape. Okay, if I just execute it, it is 128. Okay, one sentence, and for one sentence we have 128 one zeros to mask the keys of the tokens later on. Okay, so this we now are going to match with the shape that we currently have, this 112, 128, and 128. So we need to have the same number of dimensions. Okay, and they will be broadcasted. Okay, so I want to have this kind of shape that says something like 111 128. Okay, so this is the batch size, this and this. I am going to create these two dimensions. Okay, and this is the last 128, the attention mask. Okay, and I will apply this attention mask on the keys of the tokens. Okay, in each head. What I can do here is just let's test it right here. Okay, so I will take all the batch size. Okay, so let's say if we have two sentences as a batch size, I will have all the sentences of the batch. Okay, then I want to have none. Okay, again none, and finally all of the 128 values. Okay, so if I just show you this now, you can see it now matches the shape. Okay, and we can apply it right here now. So here is the forward method, and in this forward method we have now these scores. Before applying the softmax, we are going to apply this attention mask. Okay, so I will call it the extended attention mask. Okay, and this is going to be equal to, I will just copy paste this one from here. Okay, and I'll just simply paste it over here. Okay, yep, that is all. Now I want to apply this mask on my scores. Okay, so I will call it masked scores. Okay, masked scores are going to be equal to scores dot masked fill. Okay, this masked fill I will pass the mask like extended attention mask, and wherever this extended attention mask is 0, okay, I want to add this negative infinity over there. Okay, so this is what I want to add for the keys of padded tokens. Okay, now I will just show you masked scores at this point. Okay, and if I just execute it, you can see this. Okay, but I just want to show you the actual uh, result. Okay, so I will uh, print the testing. Okay, and inside testing you can see now these infinities. Okay, so the shape is 112, so I want to have just the for the zeroth sequence in the batch. Okay, and for the zeroth head. Okay, and also for the zeroth token. Okay, I want to have these first 10 dimension values, not the dimension values, these are the scores, okay, like each token against all the tokens, okay. So if I just print it, you can see we have 1, 2, 3, 4, 5, and there are these tokens, CLS plus SEP at the start and at the end. So we have 5 real tokens. All of the other keys of the padded tokens, we have now this mask that is the minus infinity for them. So when we apply the softmax will make them 0. Okay, so here I can say the weights basically, okay, and here I will just simply apply the torch dot softmax. Okay, this I will pass the masked scores, okay, and it will give me the weights. Okay, so if I just simply uh, return the weights now, I'm checking along like uh, with the each step, so we do not face any sort of received and valid combination of tensors. What am I actually doing here? I think, okay, so torch dot softmax, okay, receives an invalid combination of arguments, one of input dimension, this and this. Okay, so I need to tell it the dimension. Okay, so I am going to apply it on the like each row. So each uh, token scores will make the probabilities to 1. Okay, so let's say we have this kind of table where we have 1 0 to 127. These are all the tokens. Okay, this one row represents each token scores with all the tokens. Okay, so I want to apply it on this each row, so this each row probabilities will make to 1. Okay, so let me pass it -1, okay, over here. Now if I execute it, let's see if we get the scores. Okay, so these are the um, attention weights. Okay, at this point we have this shape like 112, like 12 heads, and in each head we have this 128 tokens and their scores, attention scores with all the tokens. Okay, but for if I just print this testing now, instead of this infinity we will have zeros. Okay, why? Because we do not want our query vectors to attend to any keys of the padded tokens. Okay, these padded tokens are the just for the purpose of making to the maximum length of each sentence. Okay, so we just added them. These padded tokens were not the real tokens. Okay, so that is why we apply this attention mask. Okay, so at this point I just want to stop here and switch here and want to show you what we have been doing. Okay, so first of all, take just this first head example. Okay, this first head example. Okay, and we will take all these query key and value vectors. Okay, so this is the qk transpose. Okay, so when we multiply this query with the keys, okay, so that is how we get them. Okay, so this is the score of token 1 with itself. this is the score with token 2. So you can see it will be something like this. Okay, token 2, and then token 3. Okay, then this token 4, token 5. Okay, so this is the form that we get, this shape we get after the QKT. So if you remember, the shape of this is 1 3 head, 5 tokens, and 4 dimension, head dimension basically. Okay, and if we just multiply it with this, so we get 1 3 5 5. So if you notice, these are this result is basically 5 5. Okay, now after this, if we just simply apply the scaling, so if you just divide this each value with maybe 2, because the dimension, head dimension is 4, and if we just take the square root, we will get 2. So we will divide each and every element with 2, and that is the QKT divided by the dimension of k. Okay, that what we have been doing. I'm just showing you. Okay, you can see this step will perform the this scaling part. Okay, so instead of these 5 by 5 shape, like this 5 by 5 matrix, here we have 128 by 128 matrix. That is the difference. Okay, so next, this is the masking. Okay, so let's say in this case the attention mask is 1 1 1 1 0. So the last token was padded token, let's say. Okay, so all of these values are going to be negative infinity, and this is exactly what we did here. Okay, using this last 128 on all the keys of the tokens. Okay, and we converted the padded tokens keys to negative infinity. Okay, and after this masking, if we apply this softmax, so this is the result of then you can say soft max QKT divided by T of k. Okay, till this point we we are done with this part of the formula. Okay, and the next step is going to be, we are just going to multiply it with v. Okay, so at this stage for our code, okay, we have 112 128 128. This is the result of this course. Okay, whereas the v on the other side, we have 1 12 128 64. Okay, so this is the with the original v shape after we generated heads. Okay, so now we are going to multiply these scores with v, and when we will multiply it, what we will get, 112 128 128, they are same, so we'll get the result 128 64. Okay, now the next step that I am going to perform here is this one. Okay, so on the weights, I will just simply call the context. Okay, this context is going to be equal to torch dot matmul, and here I will simply pass the weights with v. Okay, so this v. Now when I return the context, okay, and I just print this test, now you can see it has now the shape 112, 128 and 64. Okay, and this is what we were expecting from this step. Okay, now we have this shape. Okay, 112, 128, 64. Okay, but to concatenate them, we will again reverse these internal two dimensions, and we want something like 128, 12, 64. Okay, and these two, when we will combine them, so we will get the final result as 128, 768. So with we passed the queries, keys and values from all these multiple heads, and now we are going to concatenate them. Okay, I am going to transpose this 12 with 128. Okay, so till this point we have this shape 1, 12, 128. Now the shape I want, that is uh, 1, 128, 12, 64. Okay, so I will after this point I will just simply call context, and this context is going to be equal to context dot transpose. Okay, and here I'll transpose the first index with the second first index with the second index. Okay, so this is at first index, this is the second index. I'm simply going to call transpose them 1 and 2. Okay, and here I will just call this contiguous. Okay, and now let's test it. Okay, and see. So this, you can see now, is 1, 128, 12, 64. Okay, and here on this, now I will just simply call the view. Okay, and this view I will pass the, do I have the batch size? Yes, batch size. Okay, then the, for the second dimension, let's just skip it for now. And the last one we want is self dot head, uh, number of heads, number of heads. Let me just copy it, number heads. Okay, from here I will just copy and paste it over here, and times self dot head dimension. So simply, previously we split it, and then we just multiply them. Okay, so what we are doing, we first converted this shape to this, and then we are multiplying these two dimensions. Okay, so it will give us 768. Okay, now we have created this kind of shape 768. Okay, this dimension is unknown, but if you just pass the -1 here, it will automatically be calculated by the PyTorch. Okay, so now if I execute this, and you just notice the difference over here, uh, or if I just, for this, before executing this, I'll just copy this. Okay, and I'll just paste it over here. Okay, let me paste it over here, and you can see this is the shape 128 12 64. Okay, now if I execute this, it says 128 768. Okay, so we have again uh, the same shape of the input embeddings. Okay, so we passed the input embeddings to the multi-head attentions, and then parallelly we executed 12 heads, and finally we concatenated them. Okay, now here you must be thinking of these two methods, like why we are calling this contiguous over here. Okay, so this is where most of the people they get confused. I have some different plans for this, so I will explain them one by one. Okay, so let's say at first step we have this query. Okay, and okay, so first of all, please remember, for a view method, it is very important to have the uh, memory order equal to the logical order. Okay, one is the original memory order, and the second concept, that is the logical order. This logical order is where PyTorch basically decides on each dimension how many steps do I want to go. Okay, so let's say we have like this kind of tensor. Okay, so this is the first dimension, this one. Okay, and this one is the second. Okay, so Stride will decide if I want to go to the next dimension of on this direction. So I will have to take 4 steps. Okay, so it will take the 4 steps and enter here. Okay, but for this dimension, it if the PyTorch wants to move to the next value, so it will just take 1 step. Okay, so that is how this logical and memory order is behind the scene. Okay, memory order means memory is always in a flat, you can say contiguous memory locations. Okay, so then this logical order decides how to access these values. Okay, so for view, it is very important to have the memory order equal to logical order. Okay, so first let's say this is the memory in the RAM. Okay, A1, A1, A0, A1, A2, A3, B0, B1, B2, B3. So these are the tokens. Okay, so A0 to A3 we have the token 0. Okay, and the token 1 is from B0 to B3. Okay, now at this stage where we just create the query vector, query matrix. Okay, here we have the memory order equal to logical order. Okay, now when we called this dot view in the split head. Okay, here generate heads. Okay, so you can see here is the view first of all. Okay, so what it does, it basically converts this to 1, 2 is the sequence size. Okay, we have 2 tokens. Okay, in one sentence. Okay, and then there is this 2 heads and 2 dimensions. Okay, so for 2 splits. Okay, let's say, so we have head 0 at head and head 1. Okay, so this represents the head. Now the logical view is this one that we just created with the help of view. Okay, so this is now the token driven memory order. Okay, so token 0 goes to the head 0 as well. Okay, and as well as to the head 1. So half of the token values will go to the head 0. Okay, and half of its dimension values will go to the head 1. Similarly for the token 1. Okay, now the next step, when we call this transpose, okay, so if you remember, we call this transpose, okay, and here we are just swapping the two dimensions. Okay, so what we are doing here, we have the same batch, okay, the one, okay, but now we move the number of heads here, and the sequence length here, okay, and this is the each slice. Okay, so now with this transpose, we now have this kind of head 0, and in head 0 we have token 0 and token 1. Okay, this now underlying memory is in the same order. It is not changed. Okay, but you can see now the logical order is now changed. Okay, why? Because for the head 0, it needs to access token 0. So token 0, it can access these two, okay, A1, A0, A1. But for the head 0, if it wants to access token 1, it needs to jump from this point to this point. Okay, so here is now the logical order is not equal to the memory order. Okay, the next step, when we perform this matrix multiplication, the output of the matrix multiplication is contiguous. Okay, so it gives us a clean, fresh, contiguous output. Okay, so when we apply these kt, and then we apply this final v scores, basically we multiply it with v. So let's say this is the output we get. Okay, it is again in the contiguous memories. Okay, now again the memory order is equal to the logical order. Okay, and but here now we have headwise these locations. Okay, so for head 0 now, the token 0 is C00, C01, and token 1 is C02, just after C01, and C03. Okay, once we are done with this matrix multiplication, okay, then what we are doing, we are basically applying this transpose again. Okay, if I show you this, this is the transpose this that we perform right here. Okay, where we are again swapping the head with a number of heads with the sequence size. Okay, so with this transpose again, just like previously, now this changes to from head to token driven now. Okay, so the shape is again now batch tokens head. So these are the tokens now. Okay, and these are heads now. Okay, the dimension is again at the same point. Okay, so basically we are changing these two internal dimensions. Okay, so for token 0 now, it is in the head 0 as well. Okay, that is C00, C01. Okay, but for the token 0 now, the head 1 is going to be C10, that is right here. Okay, and C11, that is right here. Okay, so again here you can see there is the mismatch. Okay, because token 0 needs to get half of its part from this location in the memory, and half of its part from this head to from this location in the memory. Okay, so this point we do not have the match in memory order. So memory order is not equal to logical order. Okay, logical order is to move like C00, C01, and then C10 and C11, but the memory order is something else. Okay, So if you remember, initially I mentioned that this view method, it needs to have this condition fulfilled. Okay, so memory order must be equal to logical order. I am just showing you how with these calculations this memory order and logical order gets disturbed. Okay, so please remember this view and transpose, they only change the logical order. Okay, they do not copy the original data and make physical changes in the data. Okay, but when we call this contiguous, what this contiguous does, it will take the logical order and make the memory order as per the logical order. Okay, so token 0 now will have these 4 positions in the memory, and then token 1, that is C02, C03, C12, C13. So we will have now this memory order is equal to the logical order. Okay, so only in this case we can apply then view. Okay, so at this stage now, if I show you, that is why I am calling this contiguous, and after this I am calling view. Okay, and only then I will be able to give this view again to my output. Okay, so now this context, I'll simply pass this context to the, let's say, let's call it output. Okay, and this output is going to be equal to out linear. Okay, and then this out linear, we are going to pass the context. Okay, and yeah, this is the output, and now I will just apply this dropout right here. Okay, and I'll return the context. Okay, now if I execute it, I execute this as well, it says out linear is not defined. Okay, so out lin out. Okay, so sorry, self dot out linear. Yeah, now it is done. Okay, so we implemented all of these steps. Okay, q linear, k linear, v linear, and then out linear and dropout. Okay, so this is all for this multi-head attention video. I hope you enjoyed the lecture, and I see you in the next lecture. Till then, bye bye.